useful theorems that involve limits and continuity are the intermediate value theorem and the squeeze theorem. So let's look first at the intermediate value theorem. Okay. So I'll give you the formal definition first, and then we can look at what that means. Okay. Let AB be a closed interval, and let f of x be a function that is continuous on AB. So using from the last lesson our definition of what it means for a function to be continuous on a closed interval. Okay, so for all k, so remember that little upside down A means for all, and we're going to keep using that formal notation so that you can start to get used to it, because university professors will use it and not always explain it. So for all k between f of a and f of b, so the y values, so some things that are in the interval. We're not writing this one using interval notation because we don't necessarily know if f of a is greater than f of b or not. Okay, so if k is between f of a and f of b, there exists, so I'll just make sure we know there exists is our backwards e. So there exists a c that is in between, element of the open interval bounded by a and b. Okay, and it could even be, it could be a and it could be b. If there's a k between f of a and f of b, there is a c that is in the open interval ab such that okay, there exists a c that is element of ab such that f of c equals k. So essentially what that's saying is if you have a continuous function and for any value that's between your starting y value and your ending y value, there has to be an x value that gives you that y value. So essentially what this is saying, and let's draw a picture kind of to illustrate what we're talking about. Okay, so essentially what this is saying is if you have a function that's continuous and you have an a, you have a b, these are the endpoints of your interval, and you have your y values, so you have your f of b here, and you have your f of a here. What this is saying is that you can pick a random y value somewhere between f of b and f of a. So let's say you pick right here this k, and this is true for any k that you pick as long as it's between f of a and f of b on the y-axis. What this is saying is that for any of these k's, there has to be some x value, some c, so that f of c equals k. So that if we are going essentially in traveling from a to b in x, if we're continuous, it means that we are hitting every y value along our road from a comma f of a to b comma f of b, and that there's going to be some x value that gives us that y value for any point. It's basically saying continuous functions go through all the points on their way, so you hit every x value and you hit every y value as you're traveling between A and B. Okay, so how can this be useful? So this is the intermediate value theorem, which is that we hit all of our intermediate values when we have a continuous function. Okay, so what can it be useful for? Well, it can be useful for proving that you have to have a root in some areas. And you can also use it to estimate roots if you want to take some time to do that. So this is useful for proving a root exists for a continuous function in a certain region. It doesn't necessarily, it's not going to help you find the root. You can get more and more accurate estimates, but it can prove that a root exists. So how do we know that? Well, let's say we have an f of a that's below 0 and an f of b that's above 0. Okay, so we have our a and our b. So we have our f of b here and our f of a here. If we're traveling and we have a negative y value at a and then we have a positive y value at b, it means that we have to cross 0 at some point, because we have to have every k value between f of a and f of b has to get hit, so there's no way to skip 0 as we're traveling from a to b. Okay, it doesn't necessarily have to be, the intermediate value theorem doesn't say that there can't be more values. It just says that there has to be at least one, that you have to be able to travel. We could have a real, let's do a different color. There are many paths a function can take if it's continuous. We could start here and end here and do something more like this and go up and down and then way up and then back down. So that's okay, as long as it's still a function and we don't have any truly vertical lines here. That's kind of almost a vertical line, so let's make that not quite vertical. But as you can see, there's not one thing it has to do. There's not necessarily only one root. But we do know that if we're going from f of a to f of b, that we have to hit every value, y value in between there, and that there has to be some x that gives us that y value. Okay, so let's take a look at how can we find. Let's take a nice simple polynomial function. Okay, so if we have 4 f of x equal x cubed plus x squared minus 8x, we have a lovely function. Is there a 0 between x equals 1 and x equals 3? So we want to know if there's a 0 somewhere in the region between x equals 1 and x equals 3. So whenever we are trying to prove something and we're trying to use the intermediate value theorem, the very first thing we have to do is establish that the function is continuous. Because if the function isn't continuous, it can totally jump. So look at y equals 1 over x. It's positive above 0, and then it's negative below 0, but it doesn't have any roots at all. There's no zeros at all, and that's because there's a discontinuity. And so whenever there's a discontinuity, you can jump from a positive y value to a negative y value without necessarily traveling through every point in between. So f of x, remember from the last lesson, so f of x is continuous, and this is super important, and we call this established continuity, and this is the first thing you have to do before you're allowed to use the intermediate value theorem. Establish continuity. And if it's an interval, you can establish continuity on the interval, but if it's continuous everywhere, you don't even need to say that it's continuous on the interval. You can just say it's continuous everywhere, and it's also for sure continuous on the interval. So f of x is continuous everywhere because it is a polynomial. So it is important to establish that. So let's look now at f of 1. So f of 1 is 1 cubed plus 1 squared minus 8 times 1, which is negative 6. F of 3 is 3 cubed plus 3 squared minus 8 times 3. So 27 minus 24 is 3 plus 9 is 12. So we go from positive to negative. So by the IVT, there must be a root between 1 and 3. So now, if we want to approximate it a bit more accurately, we can kind of continue this iterative procedure. So we know it has to be between 1 and 3. So let's try f of 2. So approximate the 0. Let's do it a couple of times. We can kind of just keep taking something right in the middle, a point right in the middle. So if f of 2 is negative, we know the root is between 2 and 3. If it's positive, if f of 2 is negative, yeah, we know it's between 2 and 3. If f of 2 is positive, we know that the root is between 1 and 2. So f of 2 is 2 cubed plus 2 squared minus 8 times 2. So 8 plus 4 is 12 minus 16 is negative 4. So now we know the root is between 2 and 3. It's not to say there couldn't be a root between 1 and 2. It could go up and quickly back down. We don't know that for sure, but we do know that there has to be a root between 2 and 3 by the IVT. Okay, so we can try one more time. So f of 2.5 is 2.5 cubed plus 2.5 squared minus 8 times 2.5, and I'm not going to do that one in my head, 1.875. So now this is positive. So between 2 and 2.5, we're going from negative to positive, so we know the root is between 2 and 2.5. And we could keep going. We could do 2.25 and see whether the root was between 2 and 2.25 or 2.25 and 2.5. And you could keep going kind of until you had approximated it to the degree that you wanted to. Okay. So the intermediate values theorem is primarily concerned with continuity. You notice we don't use limits there. The only thing we might be using a limit for with the intermediate value theorem is that if we needed to prove that a function was continuous on a particular interval, you might need to use limits to do that proof, because that's how we establish continuity. The next theorem is called the squeeze, or I think your book calls it the squeezing theorem. And what this theorem basically says is, let's say we can't find the limit of a function at a certain point. But let's say we have g of x, which is less than or equal to f of x, which is less than or equal to h of x. So let's say we have f of x, and we can say that f of x is always between g of x and h of x. Okay, and we can also say that the limit as x approaches a of g of x equals the limit as x approaches a of h of x equals some L. So that at a certain point, g of x and h of x have the same limit. We can then say, because f of x has to be between those two functions all the time, greater than or equal to one and less than or equal to the other, then the limit of f of x has to be the same, because if they both have the same limit and f is always between them, it's kind of squished between the two functions. So then the limit as x approaches a of f of x also has to equal L. Okay? So, and a note, one cool thing about this, the functions do not need to be defined at x equals a. So they could not exist at x equals a as long as they exist everywhere else. So what does that look like in a picture? Okay, so let's say we have one function that's kind of up here, then we have one function, let's call this h of x, this was our higher up function, then we have another function g of x, it's like this, and then we have some f of x that's always between them. Okay, and at point A, the limits of h of x and g of x are the same, and so they have the same limit, which is our L, which is our y value there. So they're all approaching the same limit. So we know that f of x, even if we can't compute the value of the limit as x approaches a of f of x, we can use the fact that it has to be between the two to prove it. Okay? So let's look at a quick example. So we're going to prove that the limit as x approaches 0 of x squared plus sine 1 over x. Sorry, not x squared plus sine 1 over x. We're going to call it x squared sine 1 over x equals 0. Okay? And this theorem is really, really, really useful with trigonometric functions. Why? Because we know for sine and cosine that we know that sine x is always between -1 and +1. It never goes outside -1 and +1. So we can actually do some pretty interesting stuff here. So, okay, our starting point here is we're going to say, okay, well, we know that sine 1 over x. So anytime you see a sine or a cosine or something, we always can tell that sine of 1 over x, sine of anything, has to be between -1 and +1. Sines don't get bigger than negative. Plain old sines don't get bigger than -1 or bigger than +1. But that's not the function I'm taking the limit of. I'm trying to take the limit of x squared sine 1 over x. So I'm going to multiply all of my inequalities by x squared. And I can do that because x squared is always positive. So it's not going to change the direction of my inequality sign. So this is the same as negative x squared is less than or equal to x squared sine 1 over x, which is less than or equal to x squared. Okay? So now I have established the first part of my theorem, which is that. Okay, and you don't necessarily need to put this in your proofs. I'm just giving you a bit of a roadmap. So we have shown the first piece of our given information. We have developed a g of x equals -x squared, f of x equals x squared sine 1 over x, and h of x equals x squared. Okay, so that we have this g of x less than or equal to f of x less than or equal to h of x. So we've developed that first part. The next piece we need to be able to use the squeezing theorem is we need to show that the limits as x approaches 0 are the same. So we know, let's go and show that now. So we know the limit as x approaches 0 of -x squared is 0. The limit as x approaches 0 of +x squared equals 0. Okay, so this is part 1. This is part 2 of just showing that we have the conditions to use the squeezing theorem. So we have our functions lined up in a row. We have that the limits of both of the two functions on the outside are equal to the same thing. So now we don't have to show anything else. This is where the theorem comes in handy. If we've met the conditions for the theorem, we can just use the theorem. Therefore, by the squeezing theorem, that last step in logic, we don't need to prove the theorem, we just need to use the theorem. So by the squeezing theorem, the limit as x approaches 0 of x squared sine 1 over x equals 0. Because it's between those two other functions that both equal 0. So the squeezing theorem gives us that last step of logic to get from, we have two functions that kind of are bookends to this other function. They're on either side all the time. The functions have the same limit at this point, Therefore, the function I don't know the limit of has to also have the same limit because it has to be bigger than the one and it has to be smaller than the other. So the only choice is equality. But you don't need to explain that in that individual case. You just say by the squeezing theorem.